Today we're going to talk about the last technique of integration, and that's going to do with rational functions. When you have an integral of a rational function, which remember is a polynomial divided by a polynomial. Well, like with regular fractions, there's proper and improper rational functions. So if you remember, on regular fractions, 5/7 is proper because 5 is less than 7. 7/7 is improper, and so is 9/7 because the numerator is greater than or equal to the denominator. You can turn them into whole numbers or whole numbers plus proper fractions. So when we get a rational function and we have to take an integral of it and it's improper, like this first one, there isn't really a new technique. It's just basically we're always allowed to do algebra to simplify a problem before we take an integral or a derivative for that matter. So what we're going to do, like we can multiply, we can also divide. So I'm going to divide the denominator into the numerator. And you have two choices. You can do long division, x cubed plus 0x squared plus x plus 1. So x goes into x cubed, x squared times, then you multiply these two together, and then you subtract. So you get 2x squared. X goes into 2x squared 2x times. Now you multiply. 2x squared minus 4x, and now you subtract, and you get 5x plus 1. X goes into 5x 5 times. You multiply, and then you subtract. And this is the remainder. So that goes over x minus 2. So what we've done, we haven't done any calculus, we've just taken this fraction and converted it into the polynomial plus a simpler, proper fraction. So the answer to this integral is going to be the answer to this integral. Well, the antiderivative of x squared is x cubed over 3. Then you get x squared plus 5x. And then this last one, it's just in the form, if we put a dx right here, it's in the form of du over u, exactly. So we just go plus 11 times the natural log of the absolute value of u. And we've got an answer. Now, the second one is a proper rational function. X squared, x cubed. X cubed has a higher power than this one. So in order to do that, we're going to break it apart into 3 simpler fractions. So what we're going to do is go a, and this only works if you can factor the denominator. And you can. It's x times x squared minus 4, which is x minus 2 times x plus 2. So we're going to go a over x plus b over x minus 2 plus c over x plus 2. And the whole idea is then to make it back to equal to this. Now the question is, now it's algebraically, we're going to have to figure out what A, B, and C are. So is that going to be a very hard thing to do? I don't think so. Let's all say together how easy it's going to be to find A, B, and C. B, C, easy as 1, 2, 3. A, B, C, 1, 2, 3. A, B, C, is you and me. B, C, easy as 1, 2, 3. Okay. So we've got a way to find a, b, and c, and it's easy as 1, 2, 3. So I think we're all set. Now, because it's a lot easier than this name sounds, partial fraction decomposition, I said, yikes. What I've always done with my students, instead of calling it that, we call it Jackson 5. So it makes it more fun that way. Now I hope Johann Bernoulli, who's the one who came up with this method, in the late 1600s, member of the most famous math family of all time, teacher of Leonhard Euler at the University of Basel, I hope he feels okay with it. I think he probably would like it. He'd dance along with us. So anyway, and you are allowed to dance while you're doing these. I'm not going to do any more. As you can notice, I'm not the greatest dancer. Okay, so how do I make sure that this equals this? Well, the way we do it is to put this back under the same denominator. So I'm going to go back and put it under the same denominator that I had. Well, what is a missing? A is missing the factor of x minus 2 and x plus 2. B is missing the factor of x and x plus 2. And C is missing x and x minus 2. So if we put these three fractions back under the same denominator, what I'm going to try to do is then make this equal to this. So we really don't even have to look at the denominators. We just have to make this numerator equal this numerator. Well, one method of doing this algebraically is to, since this has to work for all values of x, just pick some convenient x's. Like if I plug in x equals 0, that wipes out these two terms. So I get what? A times 0 minus 2 times 0 plus 2 equals 0 plus 0 plus 12. So A is going to be negative 3. That was pretty easy to find. What's another nice number to put in? How about if we put in x equals 2? That wipes out this term, and it wipes out this term, and we get b times 2 times 4 equals 4 plus 24 plus 12. Or 8b equals 40, b equals 5. And one more nice number to put in would be negative 2 for x. That wipes out these two, and you get c times negative 2 times negative 4 equals 4 minus 24 plus 12, or negative 8. So 8c equals negative 8, c equals negative 1. Now that we have that, we can put these back and take the integral of these three. So negative 3, I can bring out front, dx over x. B is 5, again, I can bring that out front, dx over x minus 2, and c is negative 1. So we have three integrals to do, but they're all in the form of du over u, exactly. So to that, 5 du over u is the natural log of x minus 2, and then the last one, minus the natural log of x plus 2 plus c. And we've got an answer. So what we did there is we did partial fraction decomposition if you must, or Jackson 5 because this was a proper integral. And what we had was three linear factors in our denominator. Okay, so let's just do two more that have little bits of differences in them. Now this one has x cubed as the highest power of x, in the numerator and in the denominator. So it's still improper. So the first step we have to do is to divide the denominator into the numerator. And we have no choice. We can't use synthetic division, we have to use long division. On that last problem, I could have used synthetic division. So x cubed goes into x cubed one time. And then you multiply this times this. And then you subtract. Well, these two just turn out to be 0. So you get negative 4. So what I have to do then is replace this with this and take the integral. So the integral of 1 dx, and then you have plus the integral of negative 4 over x cubed minus 2x squared dx. And this only works, we have a proper fraction, but it only works if the denominator factors. And it does. I can factor out an x squared times an x minus 2. Now you could say that that has 2 factors, or you could say it has 3 factors. What it has is 2 factors, but one of them is a repeated factor. X squared. So it's x times x times x minus 2. Whenever you have a repeated linear factor like this, in order to give the algebra enough latitude to come up with the right answer, you've got to do a over x plus b over x squared plus c over x minus 2. That way the algebra has enough latitude that it can come up with an answer where this is going to equal the same thing that you started with, which is this. This part is pretty easy. That's just going to be x. So now we're just going to deal with this integral here. So we're going to try to make these 3 equal negative 4 when we put them under the same denominator. So I go, a is missing what factor? A is missing one of the x's and an x minus 2. B is missing just the x minus 2 factor. And C is missing both of the x factors. And we want all of this to equal negative 4. And then they'll have the same denominator. So what are convenient values of x to pick? Well, I think x equals 0 works out really nicely because that wipes this and this term out. So you get negative 2b equals negative 4, or b equals 2. And then you could try x equals 2. That wipes out these 2 factors and you get 4c equals negative 4, or c equals negative 1. Now we've run out of real convenient factors, or really convenient values of x to plug in, so we can pick any other value we want. Well, the easiest value of x to plug in there would be 1, since we've already used 0. So let's plug 1 in here. So we get a times 1 minus 2, plus b, which now we know is 2, times 1 minus 2, plus c, which now we know is negative 1, times 1 squared equals negative 4. So we get negative a minus 3 equals minus 4. Or minus a equals minus 1, or a equals 1. So now we can take this integral and make it into 3 separate integrals. So a is 1. So we have 1 over x. And then we have b to be 2. And so we might as well call this 2x to the negative 2. And then c is negative 1. So we can go minus the integral of dx over x minus 2. Now, notice I still haven't put in my 3 and 4. So I've got to keep in my mind that these are definite integrals. So I'm going to have to evaluate them all. So you get x plus the natural log of the absolute value of x. Now this one, you get 2x to the negative 1 divided by negative 1. So you get minus 2 over x, and this is exactly in du over u. So now I go from 3 to 4. So I get 4 plus the natural log of 4 minus 2/4 minus the natural log of 2. And then when I put in 3, I get 3 plus the natural log of 3 minus 2/3 minus the natural log of 1, which is just 0. So for as far as numbers, I have 4 minus 3, so that's 1, minus a half and plus 2/3, so that's plus a 6. So 7/6, and if I just take this natural log of 4 and make it the natural log of 2 squared, I get 2 natural log of 2 minus the natural log of 2 is the natural log of 2, and the natural log of 2 minus the natural log of 3 is the natural log of 2/3. And we've got an answer. And that's a number. So we solved that definite integral. Now the thing that was different about this was, one, that it was improper, and second, we had repeated linear factors. So we had to put an a and a b, 1 over x and 1 over x squared. Okay, so the last one is back to being proper, x squared, x cubed, so it's proper. The bottom does factor, and you can't factor this any further, so this is a non-irreducible quadratic factor. So we have to do something slightly different. We have to make it a over x, but to give, again, the algebra the latitude to come up with the right answer, we have to give all the possible proper fractions we could get over here. So just putting a constant isn't enough. If we put dx plus c, this is still proper, and it gives the algebra an extra variable to work with to make sure that they can make this equal the original one. So we want this to equal 2x squared minus x plus 4 over the same denominator. So we don't have to really worry about the denominators. We just try to equate the numerators. So this fraction right here is missing x squared plus 4. This factor up here is missing just x. So if we can make this work with an a, b, and a c, then we can rewrite this integral as these two separate integrals. Now this one isn't quite as convenient to find values of x to plug in here. So I'm going to show you another technique you could do. You could multiply this out, ax squared plus 4a plus bx x squared plus cx, and then put all the x squared terms together, all the x terms together, and all the constant terms together. Now, if this is going to equal this for all values of x, the only way that's going to be true is if a plus b equals 2, if c equals -1, and if 4a equals 4. Well, that's pretty easy to solve. A equals 1, and if a equals 1, b equals 1. So now I can go back and say a is 1, so I have dx over x, and then b is 1x minus 1, all over x squared plus 4. And you're always hoping for something that's going to be fairly easy to do. Well, that's the natural log value, absolute value of x. This is a little more difficult, but we're always allowed to break it up into two separate integrals here. We can make it x dx over x squared plus 4, and then minus the integral of dx over x squared plus 4. And see if we can get it into a form we like. Well, if I put a 2 and a 1/2, I haven't changed that one. And now it's in the form of du over u. The derivative of the bottom is up at the top. So that's the natural log of the absolute value of u. And then the last one. In the last talk we had, we actually took something that looked like that, and we came up with a formula. That it was, the answer was 1 over a, the inverse tangent of u over a. Well, if I think of x to be u and a to be 2, then we can use that formula. So the answer is going to be 1 over a, the inverse tangent of x over 2 plus c. And we've got an answer. So, we only did 4 integrals today, but they were fairly difficult ones. I didn't give you really easy ones. And I will let you know that if you are taking BC calculus in high school, that they only require you to know how to do non-repeating linear factors, like the second one we did, which was probably the easiest one we did. And you do have to know how to do the improper fractions that you do by just dividing one into the other. But I still think it's good for you if you're going to go off to a college to see how to do these other 2 things. They're in almost every calculus textbook there is. So anyway, you have a good rest of your day, and thank you.